So let's take a look at blood and how gases and other things are transported around through the cardiovascular system here. The first thing we need to do is take a look at the function of blood in terms of its role in homeostasis. Number one thing that blood is going to do is it's going to act as a connective tissue, which means it's going to be connecting things together. The way in which it does this is by acting as an avenue for transportation. Anything that gets transported in the blood either has to be soluble in water or it has to be able to bind onto a carrier molecule if it doesn't happen to be hydrophilic. The other thing that blood's going to do in terms of homeostatic regulation is that it's going to act as an agent to that regulatory function, in which there's two key things that it's going to be doing. First off, it's going to be involved with regulation of body temperature. One of the things that blood is going to be able to do is it's going to be able to take heat that is being built up through metabolic processes within the tissues of the body and transport it away from those tissues. The carrier proteins and the salinity and pH of the blood, the chemicals within the blood, change the specific heat of the water that is making up about 50 to 55% of blood in terms of its overall chemistry. By changing that specific heat, what it does is allows for the blood itself to absorb additional heat. Now, we have evolved in such a way so that we have a huge amount of dermal arterioles and dermal capillaries that act as a radiator for our body. And what it does is it allows us to radially release heat into the environment. But the other thing it does is that with the high density of the eccrine sudoriferous glands is that it allows us to go about evaporatively cooling our body. And the way in which we're able to evaporatively cool the body is through the movement of blood into these areas of the dermis, into the areas of the epidermis, so that we're able to go about getting rid of all this additional heat. If we cannot get rid of this additional heat, we run the risk of hyperthermia, and we have a very narrow window. We have a window of about 3.5 to 4 C window of homeostatic balance in terms of being plus minus to normal body temperature. Where if we get above about 40 C, we start undergoing heat exhaustion issues. And if we get to around 41 C in terms of core body temperature, we start worrying about heat stroke issues and sepsis, leading to death due to heat exertion. The other thing it's going to do is it's going to transport all of the hormones that are being used as communicating agents. They're going to allow for systemic and global adaptations to take place. They're going to allow for systemic and global communication in between compartments of the body. They're going to, in this systemic functioning, they're going to allow for the body to go about both its chronic as well as its acute responses that are necessary in order to maintain homeostasis to any type of stress or stimulus that are being encountered. The way in which the blood does this is based off of the components that make up blood. And so what are those components? Well, we basically have two things that are going to make up blood. We have the liquid part of blood, which is plasma. And plasma is the water plus any of the proteins, salts, and nutrients and gases that happen to be within the liquid. The other part is what's referred to as the formed elements. These are the erythrocytes, the leukocytes, and the thrombocytes. The erythrocytes, the RBCs, are the gas-carrying cells. Now, most people think about this gas simply as oxygen. However, it's more than just oxygen. We have the leukocytes. These are the immune cells. These are the cells that are going to be involved with inflammation and immunological responses to any type of damage or infection. And then we have the thrombocytes. The thrombocytes are referred to as the platelets, and they're going to be involved with vascular responses to injury and clotting factors. In terms of the total content of blood, the total content of blood is about 8% of total body weight. On average for the quote-unquote normal adults, and remember normal is based off of the normal curve, not somebody being normal. It's a statistical thing. So when we're talking about the statistical normal adult, it's somewhere between 4 and 6 liters, and we usually use 5 as the given total blood volume for mathematical purposes. However, that's going to vary based off of the total body weight for the individual. This volume is going to be dependent upon not only the size of the individual, but also the gender of the individual and the amount of physical activity that the individual undertakes. We'll get more into this issue of physical activity when we talk about the erythrocytic cycle. Generally speaking, females have a lower total body volume than males, and they have a total lower erythrocytic count than males, or concentration of erythrocytes than males. Can you think about an underlying reason for why that might be beyond just the size issue? Because for equal size individuals, it's still this relationship. In terms of blood by volume, we have a distribution of blood within the cardiovascular system where about 35% of all blood is going to be found in arteries and about 65% of all blood is going to be found in veins. This distribution of the blood volume itself is going to develop what's referred to as the reservoirs and the reservoir effects that are going to regulate vasculature responses. So let's take a look at a total blood analysis here. So what does blood look like in terms of its chemical composition and its cellular composition? So let's take a look at the chemistry and composition of blood here. So blood is going to have the same pH as the rest of the body, which means it's going to be somewhere between 7.3 and 7.5 in terms of its pH scale. So it's going to be slightly on the alkalinic side. It's slightly on the alkalinic side due to the bicarbonate shuffle that's going on within the dissolved CO2 within the plasma. By volume weights, about 90 to 93% of the plasma itself is going to be water. The remaining part of the plasma is going to be proteins, lipids, and then what's referred to as the dissolved materials. Of the proteins, the most prominent of the proteins will be the albumins, followed by the globulins, followed by the fibrinogen, and then finally enzymes. Now, the types of enzymes and the amount of enzymes is going to vary based off the individual and their set metabolic state. The type and amount of globulins will vary based off of physiological stresses that are taking place. Fibrinogen usually stays relatively low. However, fibrinogen can vary based off of clotting signals and platelet activations leading to increased fibrinogen amounts. If we look at this dissolved materials, we're looking at something that's going to be less than about 1 to 1.5% of the total weight. This dissolved material is made up of electrolytes, including sodium, potassium, calcium, magnesium, chloride, bicarbonate and carbonic acid, phosphates, and sulfates. We will also have nitrates within this dissolved electrolytic components. In terms of gases, the principal gas that's going to be found dissolved in the plasma is going to be carbon dioxide, followed by nitrogen, and then oxygen. Any gas that's in the environment will be seen dissolved within the plasma itself, simply based off of diffusion principles. So even though we talk about blood gas transportation simply on the level of carbon dioxide and oxygen, any gas that's in the environment is going to directly come into the plasma based off of diffusion, and the concentrations of those gases in the environment is going to impact the concentration of gases that we see within the plasma and within the blood. In terms of nutrients, we'll see things like glucose, amino acids, lipids, cholesterols, vitamins, and trace elements within the dissolved quantities of the plasma. We will also see waste products being taken out and transported to areas to be excreted, which includes things like urea coming from the liver, creatinine coming from broken down protein molecules and muscle, uric acid, once again coming from the liver, bilirubin coming from the spleen and from the liver. And then we have a whole bunch of hormones in circulation in very low quantities. And this is where all of those hormones that we've been talking about and how important they happen to be, they're not in very large amounts within the plasma. Even though we talk about how important they happen to be, even though we see very high spikes in hormones, the high spikes are still very, very small in terms of total amount based off of concentrations, where we're talking somewhere between 10 to the negative ninth to 10 to the negative sixth millimolars of hormones. Now let's take a look at this lipids profile and this cholesterol profile in a little bit more detail. So when we talk about blood lipid profiles, what we're talking about a measure of lipids and lipoproteins, what we call cholesterol, within the plasma of the whole serum blood. It's an indication of metabolic state of the individual, and it's highly variable within the population based off of modifiable factors and non-modifiable factors. One of the biggest non-modifiable factors that are there is a genetic predisposition to lipid metabolism. One of the greatest modifiable factors that's out there is level of physical activity and amount of carbohydrates in the diet. Now, we usually talk about lipid profiles based off of lipids in the diet. It's where the low-fat diet craze came about from. But one of the things that actually is a lower indication of having high levels of the lipoproteins in circulation within the plasma is actually the level of fat that is being consumed in the diet. Now, the more animal protein that is consumed by an individual, there will be slightly higher levels of the blood lipids. However, that is going to fluctuate based off of the amount of fructose-based carbohydrate meals that the person also consumes. Now, in terms of lipid profiles, we usually reference them based off of a desirable or optimal level, a borderline level, and then what's referred to as a high level. And so there's two references that come into play here, and you have to be able to recognize the two references. One is based off of the millimolar, that's millimoles per liter, and that's everywhere except for the United States. In the United States, we like to not use the molarity issue. We will do it based off of concentration of milligrams per deciliter, where you want to have a total cholesterol level of about 170 to about 200. You don't want to be too low, but you also don't want to be too high. You want to baby bear it, just like with everything else when it comes to physiology. If you get above about 238, 239 in terms of total cholesterol, you're starting to get into that high cholesterol level or a hypercholesteremia issue. Now, when we get to the types of cholesterol we actually want to have higher levels of high-density lipoproteins and lower levels of low-density lipoproteins. That's because the low-density lipoproteins are going to be more buoyant within the plasma itself and more apt to interact with the plasma membranes of the luminal epithelial cells within the vasculature, leading to the atherosclerotic issues. This atherosclerotic issue is linked to the relationship or the correlation between the high protein, particularly animal protein diet, and the dyslipidemia, hypercholesteremia, atherosclerotic diseases that are associated with the protein diets. And that has to do with the fact that the animal proteins themselves will have antigen markers within the proteins that get embedded into these molecules that will trigger an immunological response to the lipoproteins as they start interacting with the plasma membranes. With the low density lipoproteins, we want to be somewhere around 70 to 100 milligrams per deciliter of low density lipoproteins. If you're below 125, you're pretty good. If you're above about 160, you're in a hypercholesteremia, low density lipoprotein issue, and this is where they'll start looking at putting people on cholesterol medications. The problem with the cholesterol medications is that they will interfere with some steroidogenesis processes and can impact a number of circulating levels of steroids, and has been shown to interfere with steroidogenesis of testosterone, estrogen, and progesterone. For high density lipoproteins, we actually want to be higher. We want to be 60 to 80 milligrams per deciliter of high density lipoproteins. And this is because of what the high density lipoproteins are doing in terms of what they're moving around and how they're being passed in terms of the excretory function and what they're moving around in terms of the metabolic processes. And we'll get a little bit more detail into the lipoprotein metabolism. We look at metabolism as relates to digestion and absorption and excretion of materials. In terms of the lipids, the triglycerides, just like with low density lipoproteins, you want to be lower on the level. You want to be somewhere between about 80 and 100 milligrams per deciliter. Now, these numbers here in terms of the optimal, desirable, keep getting modified based off of the political whims of the people who are running the associations, where we've had multiple labels for optimal and suboptimal as relates to the triglycerides. The amount of triglycerides in terms of optimal, not optimal, is going to be diet dependent and metabolism dependent. People who are ketogenic will have higher levels of circulating triglycerides than people who are non-ketogenic in terms of their metabolism. The higher levels of triglycerides, if it is associated with also high levels of low density lipoproteins and high amounts of the circulating levels of glucose, then we start having to worry about issues in terms of metabolism. Along with looking at the chemistry within the blood, we also have to look at what is making up the blood as it relates to the cells within the blood. And this gives us to a new term